All right. Shh, shh, shh. So, function transformations are probably one of the things that confuse a lot of people in math, mainly because it's just a lot of rules to remember. Although for this, I would let you guys use your graphic organizer on the test. But the hard part is just figuring out, okay, which parts of the function means what. Okay? So transformations. What do you guys think of when you think of transformations? So think about a geometric transformation. If I said we're performing transformations on this square, we're changing its what? Position or shape, direction, orientation, all that stuff. All right. Can anyone name me what some transformations? There's some that you learned back in Math 2. How do I know? I'm currently teaching it. There's rotation. What else? Translation. What else? Reflection. There's one more. Starts with a D. Dilation. Good. So, translations, reflections, rotations, and dilations. The only three that we really care about with function transformations is translations, dilations, and reflections. All right? Don't really do rotations a lot in function transformations. Those are more geometric. So, the great thing about function transformations is that if you know what the parent function is, and you know what the transformations are, you can graph the function without having to make a table or anything. All right? So, this table just kind of helps us visualize all the different rules. Okay? So, the big thing about this table is that this is actually the order of which you would apply the transformation. So, the first thing you would look at if you were looking at a function transformation is the horizontal translation, which again means left or right. Which makes sense because horizontal line, if you think of a horizontal number line, you can really only go left or right. All right. Now, do not let these f of x stuff throw you. Okay, I will show you what it would actually look like in a real function. But for the most part, this is just notation where f is any function, whether it's absolute value, quadratic, linear, whatever. And then what's being affected to the x or the y, depending on where it is inside or outside the brackets. Okay? So, first off, before we even get into it, some things that I want to clear up. You're going to be hearing me say this a lot with transformations. Inside or outside brackets. All right? Now, brackets is a very loose term that I use to describe kind of its defining feature in a parent function. So remember when I said last week about defining features, those will tell you what type of function it is. So for example, a square root function, what's going to be its defining feature? What's going to be its tell? That's square root. All right, that's actually its bracket. So a square root symbol can be a bracket, which also means a cube root symbol can be a bracket. What about absolute value function? What was the tell that I said an absolute value function has? How do you know it's absolute value? The actual absolute value lines. Good. So those can be considered a bracket. All right. The other ones that could be considered a bracket, which you may see, is that technically if you're raising anything to any power, so like a quadratic, it's usually parentheses with a square on top. Cubic, it's usually parentheses with a cube next to it. All right. If stuff is inside those parentheses, then it's applying some way, and something's outside of those parentheses is applying some way. So when I say inside, outside the brackets, I mean, okay, is it under this radical or is it outside the radical? Is it within these parentheses or outside these parentheses? Outside. Is it within these absolute value symbols or outside the absolute value symbols? All right. So I just wanted to clear that up now because you will hear me saying that a lot with these. Okay. Does everyone understand the concept of the brackets? All right. So whenever we don't know what the function is, we use f of x and then whatever's being applied to it. All right. This just means it's generic. It can work for any function. So horizontal translations. It's going to be inside the brackets, first off. Now, two different ones. So as you notice, there's a plus c next to the x and a minus c next to the x. Plus c means you're going left c units. Minus c means you're going right c units. So this one is one of those where logic is backwards. All right, because if you think about it, if this was a positive number, where would you think it would go, left or right? Right. It's not. If this was a negative, you think it would go left. This is the only case where it's backwards. Mainly because there's a lot of formulas out there. So like if you recall when you guys did vertex form of a quadratic and the vertex was HK, this minus was already in the formula. All right. So that means if you put in like a -1 in for H, it'd be x minus -1. That becomes a plus. So in reality, you're still going the left, right. Okay. Now, if that's confusing you, it's okay. Just know that when it comes to horizontal, it's opposite, which you would think logically. All right. Everything else will be pretty logical, but this is the only one that's weird. Okay. So, for example, if we look at these little graphs right here, okay, right here is the parent function. What type of function is this, by the way? So it's a V-shaped graph. What type of function is that? It's an absolute value. Good. Now, this says that this is f of x plus 2. So f of x plus 2 would mean what? What direction did they actually move? They went left 2. Which they actually did. C1, 2. They moved the graph left 2 units. On the opposite side of things, this is still the parent, still absolute value. But it says f of x minus 3. So what did they actually do? What direction did they move the graph in? They went right 3. And they actually did. So 1, 2, 3. They just moved the graph over. So nothing else changes about the graph, just its general position. So that's completely a translation. It's just a slide. All right. Any questions on horizontal translations? So after we do the horizontal translations, we then do the stretches and compressions. These are also known as dilations. Now, when y'all were in Math 2, dilations typically meant you were doing what to a shape? You're making it bigger or you're making it smaller. Good. All right. So you're either making your figure bigger or you're making it smaller. Now, the vocab in this can be a little bit different. All right. So, first off, we have our vertical dilations, which come from here. Now, the vertical dilations, your C value, if you notice, is on the outside of the brackets. So outside the brackets. Now, first off, if you have a C value between 0 and 1, so if it's between 0 and 1, what type of number is it? Not between 0 and 1, it's not. If you have a number between 0 and 1, what type of number is it? It could be a decimal. What's another one? A fraction. So it has to be a true fraction. Meaning numerator is smaller than denominator. So when they say from 0 to 1, I am talking about a fraction. And I mean a true fraction. So like 1/2, 2/3. 3/2 would not fall in this category. Why? Is 3/2 a true fraction? No, it's an improper fraction, meaning it's bigger than 1. All right, so it has to be truly between 0 and 1. Now, this is called a vertical compression or shrink. On the other hand, if C is greater than 1, we call it a vertical stretch. Now, a lot of big words there, but what does it actually do? I like to think about this in terms of it makes your graph narrower or wider, depending. And I like to use hair ties, rubber bands to kind of figure this out. So let's pretend like the non-stretched version of this graph is like this hair tie. All right. If I stretch it vertically, what's happening to my hair tie? Width-wise, is it getting wider or thinner? It's getting thinner. So a vertical stretch makes your graph narrower. Whereas compression, meaning I'm compressing it. So if you look at my hair tie again, if I compress it, what's it doing to its width? It's getting wider. And that's what it does. A vertical compression will make your graph wider. Now, how would you do that? You would just multiply your outputs, so that's your y values, by your c. All right. So if we look at these examples right here, f of x is this red line right here. I know it's a little hard to see. First off, what type of parent function is this? It's cubic. Good. So then they're multiplying by a half. So did that make the graph wider or thinner than the red one? It's wider. All right. And if you notice, here's the original point. It's at -1, 1. Or -1, -1. All they did to get the new point was multiply the y value by 0.5. So that's how they got -1, -0.5. Whereas over here, red is still the original, blue is the new. So this is a vertical stretch because it's being multiplied by 2. All right, which is bigger than 1. Now, if you notice, say right here, this is the original, this is the new. They multiplied this 1 by 2, and that's how they got 2 as your new y value. The x value stays the same. All right. So you multiply the y values by c, and x value remains the same. Now, that's vertical stretches and compressions. The other one is the horizontal stretch or compression. So if you notice, our c value is right here. So is that inside or outside the brackets? It's inside. So that means there's some number being multiplied to the x on the inside of the brackets. Now, the names are actually flip-flopped, all right? But they essentially mean the same thing. And you'll see in just a second. So, fractions are called a horizontal stretch instead of a compression like it is with vertical. But let's see if it still makes it wider. So, here's my graph. If I stretch it horizontally, does that make my graph wider or thinner? Width-wise. Width, wider. All right. So like between my two hands, that's wider. All right. So even though it's called a stretch, it still makes the graph wider. Whereas if it's greater than 1, it's called a horizontal compression now or shrink, which if I do this horizontally, width-wise, what does it make it? Narrower. So regardless of whether it's a horizontal or vertical dilation, as long as you remember that a whole number makes it narrow, a fraction makes it wider, that's the biggest takeaway from these. All right. Now, the way you figure out your new values is that you would divide the inputs or x values by c. So, for example, still looking at cubic functions. Original is the f of x or the red. New is the 0.5 and b multiplied to the x. Here's the original point. It's -1. They divided this value by 1/2, which if you did change flip, keep the -1, change it to multiplication, flip it to 2/1. What's -1 times 2? -2, which is what they got here. All right. Over here, they're multiplying by 2 now. So here's the original, there's the new. They divided this 1 by 2, which that's just 1/2. So that's how they got 0.5. All right. Does that make sense? All right. Once you do your dilations, we then look at reflections. Now, the only reflections that we worry about in this class is over the x and y axis. All right. Now, be careful with the dilations versus the reflections, because if there's a reflection and a dilation happening at the same time, you may think that the dilation is less than 1 because of the negative sign. But in reality, you're supposed to ignore the negative sign because the negative is what actually affects the reflection. All right. So, first off, this first one, is that negative inside or outside the brackets? It's inside. So this one's outside. So with reflections, it's all about the negative symbol being multiplied, whether it's being multiplied to the inside or the outside. If it's being multiplied to the inside, you reflect the function across the x-axis. And all you would do is multiply the inputs or x values by -1. Another way you can write it is change the signs of the x value. So the x values, you change the sign, keep the y sign the same. If the negative was being multiplied on the outside of the brackets, you would reflect it across the x-axis. So that's horizontal. And you would multiply the outputs or the y values by -1. Or, in layman's terms, that's just change the signs of the y value. Because remember, when you're doing reflections, all right, depending on which axis you're flipping over, remember, when you do a reflection, the way you find a reflection is that you count the distance a point is from said line of reflection and do that same distance on the other side. So whatever line you're reflecting over, that x or y value will stay consistent. And then the one that you're changing would be the one that you're not reflecting over. So for example, this first graph, first off, what type of function is this? What's the parent function?
Quadratic.
Nope. It's exponential. So this is an exponential graph. All right, the red one's the original. Which axis did I reflect over, the x or y? The y. So if you look, the y-axis is my line of reflection. All you would do is take a point and you count how far away it is from the line of reflection. So this point is 1 away. You would do the same distance on the other side. So because you're on the same y value, the y value stays the same, but you're changing quadrants. That's why the x value changes signs. All right, but the y value doesn't. Whereas this one, what axis is it reflecting over? X, because the negative's on the outside. So for this one, same thing, but the line reflection changed. Now the x-axis. So you count how far away it is, which is, it's just really big, but it's actually is 1 away. So you go 1 on the other side. So still on the same x line, but the quadrants changes, so the y value had to change. If that makes sense to everyone. Heads up, my dears. Heads up or you can stand up. Your choice. The last one, and this is probably the easiest. Vertical translations. Both of these are exclusively outside your brackets. All right. Now, this is the translation that makes sense logically. Okay. So plus actually means what you would think plus means. Minus means what you think minus would mean. All right. So if I'm adding units outside, do you think I'm going to go up or down? Up. Which means minus we're going down. So this one's actually the one that logically makes sense. Horizontal is the one that's backwards logic. All right. So plus C, you're going up C units. Minus C, you're going down C units. Which you can see here. So we got another absolute value graph. Here's the original. It says f of x plus 2 on the outside, so they went up 1, 2 units. Sorry, guys, my computer's being dumb. Whereas this one, they said minus 1. Here's the original, so they went down 1 unit. So, stop. So, let's actually do this in practice. All right. So, this example at the bottom actually shows you an example of what something with the designated function brackets and what it would look like. So, first off, they said the parent function is square root of x. What's the name of that function? So if your function is the square root of x, what's the name of the function? Radical, square root, whatever. I would say square root just because radical can mean anything from square root, cube root, fourth root, whatever. All right, but if this is not a test, yeah, I take radical, whatever. So it's a square root function. So this is what they did in order. So they started with the parent function. So this right here is the parent function. They then went left 3 units, which is given by this plus 3, which you can see here. So in other words, they took the vertex and they just did it over left 3 units. They then did a vertical stretch. They said stretch about the y-axis, but another name for that is vertical. All right. They did a vertical stretch. That's given by this 2. Not the negative 2, just the 2. Remember, the negative means something else completely. So here's where they stretched it. They then reflected across the x-axis, and that comes from that negative outside of the brackets, which they show here. And then finally, they finished with shifting it up 1 unit, which comes from this plus 1. So this right here would be our final product. So in other words, this is a way that you could graph functions without actually having to make tables. Now, is it always necessarily the fastest? not necessarily. But being able to recognize those function transformations can also help you figure out what the function of a graph is without having to do any kind of weird calculations. All right. Any questions? All right, so here's what we're going to do because you got some sleepy babies in here. I'm going to give you guys a 3-minute break. You can go use the restroom. Come back, stand if you need to. No walking the halls. When we come back, we're going to do some practice in your packet together.
What do you want? Stop sleeping. I'm tired. Here's your hormone change. Hey, that's naughty language. Yeah. CJ, you wouldn't understand how hard I am. Huh? So you wouldn't understand how hard I work I am at night. That it keeps me up like this. Listen, War Thunder takes a lot of my time. It's I came up like 2:30 watching the sauce because no. I thought Fortnite, man. So how would I play Fortnite? It's really like a Fortnite. It's such a waste of time. I don't even play. I don't even play level. I'm just people. 2020.
I guess it's like you being consonants.
It's a shame he quit. Even though I've never watched a single one of his streams in my life. Huh? Are you gonna invest in Lockheed Martin? No, dude, I got stocks in Doge right now. Oh shit. I'm like stock in Lockheed and
Chase.
General Dynamics, Lockheed Martin, Airbus, Boeing, General Electric, BAE Systems. I have some of this stuff. James, and he's good. Anyway, thank you. Yeah.
Simos. Is it Simos or Simos? Simos. Simos. No.
Simos?
Simos?
Chase, I believe you're on morning, and this break was to wake you up, not to give you extra sleep time. Do you need to go get some water?
Dylan Shaman. Shaman.
Get up and walk, get some water.
Sham.
You tired?
Man.
Get something.
All right, so take out your packet now, and let's start. Go to page 8. We're going to start there.
You should snore inside your hand.
All right, so we're on page 8 of your packet. We're gonna start seeing if you can recognize the transformations from the function. All right. So page 8 of your packet. So take a minute, look at the very first function. All right. Let's go with Dylan. What type of function is in the first one? What's the parent function? It's quadratic, yes. So it's quadratic because it has that square. All right. So parent function here is quadratic. So if it's quadratic, that means your brackets for reference are the parentheses. Okay? So your parentheses are the brackets that we're using for reference. So we're going to go in order of horizontal vertical transformations. Or order of transformations that we just did on your graphic organizer. So we're going to start with horizontal translations. All right? Look at your function. Okay? Let's go with Autumn. What number in this function tells me my horizontal translation? 2. So not the translation. That shows the dilation, though. So which one shows the translation?
I don't know.
Well, what is the horizontal inside or outside the brackets?
Inside?
Okay, so the brackets are right here.
So it'd be 1?
It'd be 1 because you're adding it.
Okay.
So translations, you're always adding or subtracting something. Okay? So it's +1. So Autumn, what does that mean in layman's terms? So in words.
If it's +1, then go left.
Mm-hmm.
1 because it's really a negative.
Good. So left 1. That's the first thing you do. Okay? Now, any dilations? All right, let's go Jonathan P. So, dilation. What number would tell me my dilation? Nope. The dilations you're typically adding or subtracting something. Not adding, subtracting. You're multiplying something. What's the only place I'm multiplying anything? The 2. All right, so the 2 is my dilation number. Someone, yeah, go. There's a new Delta messages.
Okay.
So, what type of dilation is it? Let's go with Shakib. So, what type of dilation is it? So, where is the 2 located? So, it's inside. That means it's a what dilation? Horizontal. What is it specifically? A stretch or compression? It's compression. So it's a horizontal compression by a factor of 2. Because remember the hair tie? Horizontally, if you compress it, it gets thinner, which is what we want for numbers like that. All right, so this is a horizontal compression by 2. Do we have a reflection? Is there a negative anywhere in this being multiplied? No, there's not. Typically, the negative will be multiplied to the dilation or be outside of the brackets on the left. So there's no reflection. All right. Lastly, we got our vertical translation. So, Jonathan M., what's my vertical translation? Or what number gives me that, first off? It'd be -4. That's the vertical, because it's outside the brackets. And what are we doing specifically? Down 4. Good. So, guys, that's how you go about breaking apart a function and actually labeling out all the transformations. All right? Let's try another one. So